Hello. Sorry. Thank you for coming for the afternoon session on a Friday. I guess because everyone just eaten and I'm the first one, it's my job to wake everyone up. I'm Andre. I work at Glaive with Sanzi, Jade, and Dylan, which is a research group here in Glasgow. And I'm going to talk to you today about APIs or application programming interfaces. First, I'm going to go through what it is that I'm trying to solve, what is the problem, how to describe it, and then what is the appropriate solution for it. And that solution is Stellar, a library to solve the problem that I set out to describe. So an API can mean many things, right? Those words, they're overloaded depending on the domain in which we're working. In general, it's about different programs that communicate with each other, that have an advertised interaction layer, and then other programs that will use this interaction layer to interact with them. So as an example, we're going to say there's a program 1, and program 1 will interact with program 2. Program 2 will get the interaction of program 1 and then interact itself with program 1 again. This is, of course, not real. There's no single software in the world that works exactly like this. There are many layers of complexity, abstraction, implementation, hardware. What we want to talk about exactly is what is the interface between those two programs, whatever it is, whether it's hardware, software, a description, a file format, anything. One of the reasons the word API is overloaded, or one of the domains in which API is overloaded, is the domain of web development. So if you are doing web development and you hear the word API, what that means is HTTP endpoints. And HTTP endpoints is a way to describe an HTTP request by saying what it is, what it looks like, what are the data that it's carrying, and what is the response, what is the data that it's carrying back, what it's received by the server that is sending it back to the client. So in here, I've displayed two kinds of HTTP requests. There's a GET request that sends very little data, essentially what file path you're looking at, and what you'd return is, for example, here, a list of items. Or a POST request would have maybe some data that will carry a payload, and the server will respond with a yes or no saying your payload has been properly uploaded or not. There's another form of API that's operating system APIs. What it is that you need in order to communicate with the operating system. So in this case, program 1, like we saw before, is any user space program, and program 2 is the operating system. And here I've taken as an example POSIX. Operating systems are really big, really complicated, and so there are different ways that the specification takes form. It can take form in this, it can have the form of a C header, for example, saying, are you implementing libc, yes or no? It can be in the form of, here are some command line utilities that I expect to be able to use, or here's some primitives that the operating system needs to have to perform operations such as interacting with files, interacting with processes, creating processes, etc. What we see again, and I've put in gray here, is that there's a common form with web APIs, which is if we take a C header, a C function prototype has a name, it has a list of arguments as inputs, and it has a return type as outputs. Not shown here are what effects those things could do, but that's good enough as an approximation to see what's common between a web API and an operating system API. A command line program similarly has a name, it has a list of arguments, and the outputs, we all know it, it's a string. Command line interfaces only output strings. They also have side effects, but mostly the only thing you can see is a string. So we can see it as is a relation between a series of arguments and a string, an output type string. Primitive operations like process primitives are more complicated because they will have an implicit protocol with them, which is you're supposed to create a process, use its process ID to perform operations on it, and then once you have it, you can stop it or change it, pause it. So those interfaces are much simpler, but they're much simpler in surface because they don't take any arguments, and their outputs is also trivial. It's just nothing, but everything is in the side effect. Finally, a database also gives you some form of API by saying the database schema itself describes what it is that you can do with the data. What data can you query? What data can you expect from it? What migrations make sense in this context? And generally, how can you manipulate the data that is stored? What is in common in all of those APIs is the notion of sending a message. More than sending a message, it is paired with receiving a response for that message. That is, again, a very intuitive or a very obvious way to do it, or to see this. Multiple research results or implementations have done this before. What we're going to do that is a little bit more interesting is that we're going to index the response by the message. And many people will recognize this as a container. Now, why are we working with containers? Well, we are working with containers to allow describing those APIs, but more specifically, containers in particular containers in particular have enough monadal products that we can use to describe combinations of APIs, combining multiple of these APIs to build a larger API. This is very important because one of the things we want to do is use a co-product of APIs by saying, I'm exposing an API, but I'm exposing a choice of actually two APIs. Either you can call this one and get the response for it, or call this other one and get its response. If you look at a web API as a list of endpoints, not only you have the input for each request you send and the output for each request you receive, response you receive, but the entirety of the server or the entirety of the endpoints can be summarized as a big co-product of multiple endpoints, saying my API is just the co-product of the get endpoint, the post endpoint, the other post endpoint, etc. And in this way, we can internalize and remain in the same domain, saying every API is a container, and then reuse all the categorical structure that we know about containers. There are more complicated APIs like we've seen. So this is a file system API where the input-output relations are very simple, but there is an implicit side effect here that is not represented. But we would like to represent this as an API saying a valid way of interacting with this file system is a combination of those APIs. So in some way, we need to open a file so that you give it a file name and you obtain a file pointer or a file handle. Given a file handle, you want to read the file, so you get a string back. This is the second one. Or given a file handle, you want to close it such that you're done with it. Nobody else can read it, modify it, etc. What is the model operation that we need to use here to combine those things? Well, first of all, let's make clear what we need. We need to be able to say that you cannot read a file if it's not been opened before. You need to open a file before you read it. So there's a notion of order here that is important. You cannot close a file twice. That is somewhat obvious, but there's a notion of linearity here. Once you've spent the pointer, you can't use it anymore. And same thing with open. You should not be able to open the same file twice, otherwise you get data races. One way to do this is to use what is confusingly the composition products of polynomial functors, but I'm just going to call it the sequencing products on containers, or the sequencing product on APIs, saying a valid API for a file system is you must first open the file, then you must read it, then you must close it. And no other instance of this makes sense. One problem with that is that it will force you to read the file exactly once, which is not really always what you want. So there's an extra operator that we can apply on containers by saying, you can read this file either 0, once, or many times, and then close it. And that's the entire API. So you can only open the file once because there's only one open. You can only open the file, openly close the file once because there's only one close. And you can read the file as many times, including 0 times. I've said earlier that one of the benefits of this approach is that you can reuse all the knowledge that we've acquired from the categorical structures of containers. one of which is container morphisms. How do you compose those things? What does it mean to compose them? We're missing a couple of slides here because I've done this in a hurry, but this slide contains all the information that you need to build large programs, large-scale program, by saying a program that is described by the API A1 can delegate its work to another program with API A2. So this program, what it does is translates messages from things that it receives to messages that another machine can handle, and then translate back responses from A2 back to A1 and send them to whoever asked for the original message. To understand this, to understand how to use this to architecture programs, we're going to look at a typical program, which is quite complicated, but is summarized here by saying, let's say we have an entry point for a program. There's a first box here that handles maybe the arguments that you've given it. Let's say it's a command line program, and it needs to do some parsing, needs to return some files, maybe some early return because you have to handle errors. Once everything's fine, you will go to a main box that contains the business logic or whatever you call it, that does all sorts of effects like is summarized here, including maybe calling to a database, maybe calling to a server, maybe calling to multiple servers. And once you're done with your logic, you will maybe package your data in a format that makes sense. Maybe you're going to put this in a frame buffer, display it to the user, or maybe as a string because you're a command line command line interface, and then produce some output. What we're going to do with this is we're going to take this program, think about the side effects a little bit. Well, remove the side effects rather, rotate it 90 degrees, rotate it again, line up the output with the input. And what we have is we've reconceptualized a linear program as an API-based architecture for the same program, saying the API of my program is what it takes as entry point, what it produces as output. Its layers are ways that the internal different APIs interact with each other. So the first layer is, let's parse this input and let's print this output. The intermediary layer, all the messages that we understand for the business logic. And in here, we can add some little extra arguments saying, maybe there's some side effects. So maybe there's a error monad here that will say, oh, in case of errors, do not carry this forward to the main logic. You don't need to, you can return early. And you would imagine an arrow going down here and saying, now produce the output. And once you're in the main logic will say, well, sometimes I need to interact with the database. So this is another container morphism saying we're going to interact with the database here, or there are some other API calls to other servers that have to do. And then you can reuse the same language using operations on containers to express exactly what this main logic will do in terms of delegating more work to other subsystems. All right, we're getting towards the end. So what I have done is I've put all those ideas, packaged them into a library that you can import in Idris by writing those 4 things. There are 4 sub-libraries of what they do. The main one is Stellar API that describes all the generic combinators for both containers and their morphisms. There's a version for instantiating servers, so that's parsing HTTP requests and passing them along to something else. There's a library for handling SQL queries, well, SQLite specifically, that takes some data and generates queries for them, and then calls the database to obtain some response, and someone to do the same thing on the browser side. All of this to say that today you can write a program not just in a linear sequence of steps, but in terms of this API-based architecture, saying my program is not just this linear sequence of things that happen, but it's a different slices of how to perform API transformations, how to delegate work between modules that take input and outputs. So an entire program that, for example, is a web page or a mobile application would have a front end that would be a container morphism from a user interface to the web API. A backend would be another morphism from the API to SQL queries, and the database would just be executing those SQL queries. That's me. I'm done. Thank you for listening, and have a good, I don't know that.